about emergence of space-time in string theory. And I want to start this presentation giving to you some basic mathematical facts about string theory, because I think that knowing them, it would be probably kind of boring for those who have already familiarity with string theory, and it could be, on the other hand, useful for those who have not. And to see these few things would be very, very helpful to understand how a notion of emergence of space-time in the theory can be formulated in a way which is rigorous. Because this notion of emergence is intrinsically a mathematical notion. It comes out from the mathematics of string theory. And thinking conceptually about emergence of space-time in string theory is, after all, a way of reading the mathematics. So I want to share with you some basics that will help us to find an orientation in what I'm going to develop in the second part. Okay, so just a few words of very broad introduction. So string theory is, to me, an interesting quantum theory of gravity, because it is both self-consistent and it can make at the same time a good contact with low energy physics and unify quantum mechanics. It has fermions. It has a lot of good aspects. And but let's say that it has also some. There are also some problems. Okay? There is a list of good things and a list of bad things, in the sense that, on the other hand, it is an incomplete theory in some sense. So there is no, at least many people are working on that, there is no exact formulation of the theory. The theory is developed in a perturbative regime, in weakly curved space-time. Some people are working with highly curved space-time as well. And also there is another issue there. As you know by now, because we've been talking about extra dimensions, right, for the first 2 weeks. String theory requires extra dimension, compact extra dimensions. And this extra dimension the reason for which we need extra dimension is something that we will understand during this talk. Because later on, in a few minutes, when we are going to quantize an open string, this is going to happen in 10 minutes, and don't be scared. But I think it is absolutely useful. The reason for which I'm going to do this, you will be able to follow it. We will understand one of the main reasons for which string theory needs extra dimensions. But another reason, among the other reasons, there is also an historical reason, because the idea of introducing extra dimension is it has been always a useful idea in physics, right? I think the first guys who came up with this idea were Cruz and Klein. If I'm not wrong, it was about 1920, right? So they were trying to unify electromagnetism and gravity, and they came up with this useful idea that, okay, these could be two four-dimensional theories arising from a more fundamental five-dimensional theory. So, and this idea reemerged in string theory. So it has not been introduced for the first time in string theory. But also these extra dimensions, why compact, right? Why compact? Compact in mathematics, the definition of compactness used in string theory is the same as in mathematics, but it has an additional meaning in it. It also means small, okay? So if you study the definition of compactness in mathematics, it doesn't necessarily imply that a compact set is a small set. But in string theory, it is this additional, yes.
Why don't you explain what compact means in mathematics? It means that all limits are
There are
contained
tons of definitions. You can say, well, you have a topology, right? So the notion of compactness is in relation to a notion of topology that you give on a set. But that's a good point, because not everyone knows the notion of compactness. So you can say that a subset is compact if, with respect to that topology, is closed and it is bounded. So it has a boundary, okay? I guess you don't want the exact mathematical definition.
Well, the usual definition is that it contains all limits.
Exactly, that's what I was going to tell you. So when I said it is closed,
Right.
There are
Closed
people who use the
short
notion of
set.
density, for example. But when I say it is closed, what I mean is that you take a sequence of elements of that set for n that goes to infinite, a sequence in this set, by natural number, and the limit to which the sequence converges is another element of the set. So you can't go out of the set, okay? So closed and bounded, with boundary. But doesn't necessarily imply small. But in string theory, we want this compact tensor dimension to be small, curled up with a very tiny radius.
Sorry, I missed the word. It doesn't imply that it's...
Compactness in itself has a topological property. It doesn't imply that something is small.
Is what?
Small.
Oh,
Small.
small.
I'm sorry.
Right,
It's
okay.
my horrible Italian accent. I will try to write down. When you don't understand, raise your hand, and then I write down the word on black. That's if I get the spelling right, hopefully. Otherwise it's hopeless. Okay, so the theory wants to be phenomenological respectable, right? So we don't see this compact extra dimension around. So, but they are very small. You can't detect them. But they have very, very nice properties. They can answer some mystery in the physics. Some of the mystery of the particle physics, like why there are out there three families of fermions, distinctive just by heaviness, or things like I don't know why there is continuous braiding symmetry, and this compact dimension seems to be an interesting account. So, but the problem with compact dimension, and then we will start with the more, let's say, more interesting, more mathematical stuff. The problem with this compact extra dimension is that apparently we don't have a unique choice about topology of this compact extra dimension. What I mean is this. There is a problem of underdetermination. It's something like the Poincare problem of underdetermination, of the geometry by empirical data. There are topological different compact extra dimensions that, despite that they are very, very different, they produce the very same low energy physics. And this compact extra dimension can be, flatly speaking, well, it's a family of Ricci flat manifolds. Ricci flat, we will see this. And there can be toroidal compactification, well, torus of dimension 1 is just a circle, right? There can be Calabi-Yau manifold. I'm not going to draw a Calabi-Yau manifold here. But in both cases you have dualities. In the first case you have T-duality. So the two compact dimensions with different radius, they produce the same low energy physics. It's because winding moments of the string, the switch with Kaluza moment, and things do not change. But okay, this is irrelevant. Yeah.
I just want to make sure I understand that
Yeah,
the way you're describing it, it doesn't sound like a principled, a fully principled underdetermination. That is, if you were able to probe at extraordinarily high energies, that would reveal differences between these different.
Some people give it depends on how you read duality. It's not, you are right. You are right. In the Poincare case, there is no way.
Right.
Poincare said it's a conventional choice.
Yes.
Yes. You're right. No, this is very useful. Some people think in that way about dualities.
I see.
There is no correct geometry of the
You seem
world.
careful to just restrict yourself to low energy behavior.
Right.
When you were talking about the equivalence.
Exactly.
I took it that implied that at higher energies they might be different.
Yeah, at high energy, yes, they are the different. They assume to be, because we assume in the existence of these extra dimensions.
Sure.
There is no empirical data.
No, but if they were there, they would be different.
They would be
high
different.
energy behavior would depend on the
Yes,
topology
exactly.
of convection.
But some people say, no, look, this duality doesn't. There is no correct geometry in the world. Some people say there is no geometry in the world because you can read duality in a way which produces some kind of background independence of the physics. Physics don't care about metrics. And the physics which is produced, but this is another issue. They may not come out if I be able to reach the end. It could come out with the DSCF-fatigue respondence, which is wide. So that's why I'm saying things very, very shortly. Okay, so now you have a list of good things, a list of bad things. Let's move to something more. Let's see. Let me see here. Well, I can skip this. All right. Let's move to something more. I want to give you some basic in mathematics. So I apologize for those who already know this, but I want everyone is with me. Okay, I will try to not to lose any of my people here. So what I want to do is this. I want to show you as much as I can in a very simple way how a closed string, because I actually didn't say anything so far about the ontology of the theory. What do I mean when I say particles are strings? This is the ontology of the theory. Okay? So strings are the primitive ontological elements here, populating this domain. And what do I mean with that? Okay, I think that the only way in which we can figure out that is to see how mathematical this comes up in a very basic way. And I want to show you how closed string produce gravity. And then we will move to something else, which has to do with emergence. Okay? So let's start very, very easily, right? I'm going to start here, so something will be kept, or something will be erased, but tell me, can you, all of you see clearly? Okay. So we have here a variable, let's say from 0 to pi. We have a variable, an angular variable. Oh, I forgot to give 5 bibliographic references about this part. I want you to have this. So one is the fantastic Zwieback. I'm based on this bibliographic reference. The other one is Becker, another Becker, two Beckers, Parker and Pigot, and Schwarz. I remember it correctly. And then there is, I really strongly, Saskin, encourage you to watch. I did it some time ago. The classes of string theory that Saskin put on YouTube, they are just awesome. He was here last week, he did a lecture on that. And there are things on which I really rely in of this video, you will see later on. Because I think he had a very, very nice, brilliant way to give a model of representation of some string dynamics. And it helped me to unpack very easy stuff to a very basic level. So I encourage you to start with this if you are interested, and then move to this, which is more advanced. Okay? Okay, so, yeah. I heard the question? No. I'm sorry. I think it was just covered. Okay. So we have a function. Imagine a function of, let's call this something like that, okay? And let's imagine, let's see. We can think to a string, for now, as a basic notion, like the continuous limit of all these points. And what do you mean? If you have a function like this, you take here sigma I minus 1, and here sigma I, and so here there is a delta sigma, right? So the string can be seen like a continuous limit of this point coming always closer and closer, with the limit that delta sigma goes to 0. And what you should do is think to each of the point here, like if there is an harmonic oscillator sitting on this point, doing all the time back and forward, vibrating. So continuous limit of this little massless harmonic oscillator. And I'm going to say, what is an harmonic oscillator? How many people know what is an harmonic oscillator? A lot of people, right? So the classical harmonic oscillator is this one, for those who didn't raise their hand. Okay, I'm writing. It's a system that if you apply, well, a spring, right? A spring. If you apply a force, you will experience, if you move the spring, not string, sorry, from the equilibrium, right, it will experience a restoring force that will be proportional to the amount of the displacement, okay? Okay, this is a way of representing an harmonic oscillator. So now, functions like that in mathematics are usually represented like the convergence of Fourier series. How many people know Fourier series? Oh, good, good. That's fantastic. I feel much better now. Okay. Let's see. Let's write down this one. And what do I mean with Fourier series for those who sigma? Or you can have another one with cosine, or you can have a combination. There is everything. So let's cosine and sigma. I'm not going to speak about boundary condition. We know there are two families of such dysfunction, usually and normal. But we are not going to use it. So this is stuff you can find on the text. So what it is? Okay, this is the Fourier coefficient, right? And you see there that I have hidden something. Because I'm very lazy, I'm expressing the dependence just on sigma, but there is a hidden time dependence, right? Which comes from these, because they are harmonic oscillator and they oscillate through time. But let's leave like that. I mean, it's easier. It's a much more. But okay. So we can think, why am I doing that question? Why are you talking about Fourier series? Well, because I want to introduce the notion of worldsheet to the string. Okay. And for now, I mean, you have a string which is, let's stick to a string embedded in space-time. Okay. And this string is moving, not just oscillating. So it is oscillating, but also moving along time. And the string worldsheet is a surface. It's a two-dimensional surface because we have two parameters here. Okay. I just said, let's think for a moment to the word surface of the string like a surface embedded in a three-spatial, well, in a four-dimensional space. But let's think just to the spatial part. Okay. But I want you to keep in mind this for me, in the back of your mind. This is not an intrinsic perspective of this theory. Okay? It's something that looks like it is an intrinsic feature if you read the classical string theory, the classical formulation of string theory. But there is something to say that has to do with emergence of space-time.
What's not an intrinsic feature?
The fact that the worldsheet has to be necessarily conceived as an embedded surface in space-time.
Oh, okay, good.
Is that so far so good? What I mean is that this embedding in space-time is not something that the theory requires. Okay, it's for pedagogical reasons. Is that pedagogical? Okay? Does the word move?
Yeah.
So okay, they are called, by the way, Riemann surfaces. They have a lot of nice properties. Okay, let's do this now. I want to check my notes. I don't want to skip anything. All right. I want to do this. This is X. This is Y. And this is Z. And I want to quantize an open string. How is it is work? It's so difficult? No, it is not difficult. And I show you why I want to. What nice things we will get. Oh, there is a string here, and this string is moving along the z-axis. Okay, it's an open string. And I'm now going to. Well, by the way, we want relativistic strings. Okay, so this string is moving along the z-axis with a very, very high speed. Okay, and I'm now using a very brilliant way in which Professor Sassakin, described the motion of a relativistic system in a way that it is not relativistic. Sounds weird, right? But I'm using one, yes.
Let me just make sure I understand what you're saying. So I'm supposed to think of the string as a string of little harmonic oscillators.
Yes.
Yes? You
But
talk
they
about you talk about the string moving through.
Yeah, because they
through
don't
space.
just oscillate, they also move through
Good.
space.
So
They
I should, think
translate.
of I should think of the centers of the harmonic oscillators translating through space.
Absolutely.
And at the same time, so the
Oscillate.
center of mass, their center of mass is sort of moving through space.
Exactly.
And at the same time, they're changing positions relative to one another via these harmonic
Exactly,
oscillations.
exactly.
Okay.
And this is absolutely useful. I'm going to give you an easy representation of this state of things, okay? And yeah, because they oscillate, but they also move. I can reproduce this, okay? But with my hands, but well, I am Italian, so I will sorry, I will try. Okay, so this string is oscillating, but also moving. Very high, very, very high. Now, the problem is that I'm not going to talk about relativistic oscillation. This is a relativistic object. It's just impossible. I have no idea if other people out there are talking about relativistic vibration of strings. I think it requires a lot of machinery, and this is not the case, right? So I want to use this idea that Sasaki presented, and also Zwiga, which I don't have here. So the idea is this. And this is a peculiarity of string. If I have a string which is moving like that at high speed, what happens is that when I go to study its vibrations, the oscillation of each of these infinite harmonic oscillator, I can represent that motion just on the plane through a model which is not relativistic. So, in other words, I'm using the infinite momentum reference frame. In this frame, you have the chance to study relativistic system with in a lower, something about the relativistic system in what you need. In our case, we need to study the oscillation. We don't need about translation, because that's the whole thing about particles, okay? We need to know how this oscillation works, how they produce particles. So, but there is a way to, using this infinite momentum reference frame, okay? We have the chance to study what is called, the projection of this oscillation over the xy plane in a way which is not relativistic. So we are back to our familiar quantum harmonic oscillator, and we know a lot about their physics. And it's a peculiarity of this thing. It's whatever happened to the oscillation along Z, it's all encoded here in a lower dimensional, non-relativistic model. And as Sasaki emphasized in his video, this is not an approximation, okay? It's an exact representation. Okay, I just want to write down something that it will be useful when you are, it will be useful and it takes some time to derive. It's not very difficult, but in an infinite momentum reference frame, we have the masses. The energy of the string is equal to the square of the mass. This is something that Sasaki derived, but you can derive this from this, the famous relation that everyone knows, right? So you make P very, very big, and you bring out the square root, Cotillion approximation, and you end up with something like that. And this is going to be, okay, let's keep it. Also, let's keep that. Well, we don't need in the rest frame, okay. So maybe later. Okay, so let's start to see now. Yeah.
Are we supposed to think of this string as vibrating, the oscillations as being in a plane, and that plane is moving at some angle?
No. The plane is the XY plane, it's there. And
no, not that plane. I'm just saying, on your picture on the left, the oscillations are taking place in a plane,
yes.
And they're, presumably, you're not allowing for the strings to twist out of the plane.
Yeah, this is just a bidimensional picture. Yeah.
Is that the same thing over here or not?
Yeah, that is okay. Let's say that. That is, in some sense, the bidimensional projection of what you have here. Here, the string is moving along Z, but also every physical properties concerning oscillation and physical dynamics concerning oscillation is projected here. But don't take that too seriously, in the sense as a representation of a string. That was just a way to use it up. Yes?
So the string is moving along the, is it oscillating in x, y, and z?
It is oscillating also about z, but there is a point here, a peculiarity of string. Whatever about oscillation happen about z, it's perfectly encoded on x and y plane. It's what I'm saying, we can study the oscillation of strings in a lower dimensional space. Holographic property of string or something like that. We will be back, yeah, hopefully at the end of this section. Okay, so let's think. So we said, okay, harmonic oscillator, but we want to do quantum mechanics, and let me see what I want to leave this, but I can get rid of this. And now, what I want to do is promote these guys to operators, right? This is what we do in quantum mechanics. And, well, you have a classical harmonic oscillator. Do you think it would be useful to refresh how to write Lagrangian or not? No answer, yes answer? Okay, I'm going to potential energy, right, kinetic energy, frequency of oscillation. What does it mean, xn? Xn is just the coordinate of the single oscillator, which is oscillating to the frequency energy. So here we know very well how to get momentum, which is, sorry, this is n, this is refresh, right? It helps. Then we have an Hamiltonian, this is what I want, the Hamiltonian. I'm skipping everything, but I don't think you guys want to have a class on how to get the harmonic, the Hamiltonian, right? This is not a quantum field class. So let me write this. I'm trying to write the minimum things you need to understand what we are doing. So this will allow us to, now this is promoted to operator. Now the Hamiltonian acts on the states, and I wanted this guy act on the states, because acting on the states, basically there would be the production of, well, production, I don't know if this is the right word, but it has to do with spectrum of states and particles showing up in this spectrum. Okay, so I'm going to say that this is, you know, you learn in quantum field theory that I never remember which one is A minus, so just let me check. Okay, A minus is with the positive. So this is the, now this is the operator, this is annihilation and creation operator. And you know that when you are working in quantum field theory, any observable, any operator can be decomposed in annihilation and creation. So it's easy. So, okay, so once we got here, I'm going to skip this, otherwise I won't. Using this, you have a way to rewrite, and this is important, the Fourier coefficient now in the operator of the in operator that which are the quantum harmonic oscillator. And this is okay. I have a plus. I'm going to give you here plus A minus BC scale n and yn is this one. I'm using x and y. Okay, 2 dimension. And for y, I'm using b. So we don't get confused. Okay. Now they are operators. They are quantum harmonic oscillator. And now I have just to replace here in x and y. So let me just rewrite this. This is, and let me just write this, and we will understand now why this is important. Where is it? Okay, A plus n, A minus n, and then Bn plus minus n. Of course, cosine and sigma and cosine. Now we are choosing cosine. Okay, this is an open string. Okay. So you see now, when people say, okay, particles are strings, and there is always people use this metaphor, the violin string that produce notes. So you see now mathematically how it works. There are these harmonic oscillators, they are now creation and annihilation. And so they just take the ground state and put a unit of energy if it is creation, or it kills if it is annihilation. So it takes off in energy. So this is the relation, right? You know, V like is going to be, let's say 1. Okay, V plus 1. If it is 1 minus V, it's going to be V minus 1. Take off a unit of energy. Why do we, so let's try to see how we can produce a photon. We can have a photon in the spectrum of an open string theory, okay? And this would be useful to understand first, because why do we need extra dimension? And second, this would make very, very easy to understand, to see with your eyes how gravitons are produced by Cruz strings, okay? With an analogy. Because we can think of gravitons, and this is, oh, sorry, I kept talking, sorry.
So I was going to ask 2 quick questions. One is, so the m squared that's, so equals m squared, that's m as a...
String, the whole string.
That's the frequency of oscillation of the string.
I'm sorry, say it again.
That's frequency of oscillation of the string rather than any kind of mass, just to check.
I think this is the mass of the string that, I'm sorry, I think I didn't get the question. The mass of the string. Oh, you
So
mean whether
he's asking, the expectation, the normal expectation
Yeah,
would be
sorry.
that the energy would have something to do, the energy of the string would have something to do with the way it's oscillating.
Absolutely. Yes,
So,
yes,
so
yes.
M there is some measure of frequency of oscillation.
Yeah,
Right.
well, the energy increase if the harmonic oscillator started to increase their
Right.
frequency.
So the little m in that equation
Yes.
must refer somehow to such frequencies.
Yes, it
Yes?
it depends on.
Good.
I mean, the more they oscillate and the more the string become massive
Good.
because the energy become huge.
Sure, but
Yes.
But its meaning is mass.
Its meaning is mass, but the string,
Yeah,
its
the
meaning,
relationship
it's
to
mass
mass.
of a physical, yeah, I mean, it's a physical mass in the sense that it is energy. Yeah, well, yeah,
Okay.
But I think here's what he was asking.
yeah. So,
You might have had a
Thank
naive
you.
model in your head of these harmonic oscillators as little masses on a string.
oh!
And you might have thought that this mass was referring to
like the
sum of
summation of all the mass
Right,
of the
right,
harmonic
right.
oscillator.
Right, and that's
Oh,
not.
that's- Oh,
Right,
thank you,
right,
Daddy. Thank
right.
you. Stay here until the end of the class. You have to help me to translate. No, that's my fault. It's not your fault. I mean, I just misunderstood. Okay, I know. Okay.
Right, and
can
you did say that they were massless, right, harmonic
Right.
oscillators, right.
You can think to a situation like that in which you have all this mass and springs, and they are all oscillating. Yeah. Well, think to this. Well, you can think to this. Let's reformulate what I said earlier on. When I say the continuous line, you can think like a string, like, yeah, a collection of this point with the mass of some kind, okay? But then, you define the string like a limit, a continuous limit of this point, which gradually become massless. When I say point, I'm actually using not some kind of physical entity out there or natural kind. Point is an abstract notion, is a mathematical point. When we say, I know that I told you there is an harmonic oscillator oscillating, okay? And so you think, okay, that is a physical system, but it's a bit like the notion of center of mass, which is an abstract notion, it's a mathematical notion, right? It's not a center of mass of the body, it's something that exists over the body or in some sense it exists as a particle exists physically in reality, as exists this chair or the atomic components of this chair. Is an abstract notion. So you can think of this harmonic oscillator like massless.
So the M throughout and all the various equations is representing the frequency of the harmonic.
Exactly. So you don't have to think to the M like the summation of all the M's of all the infinite points which are oscillating. But you have to think to M like a quantity which is frequency dependent. The more each point oscillates to higher frequency, and the more the string becomes massive. Does it help?
Yeah.
Okay.
The other question was just, does each oscillator have a unique frequency?
I'm sorry?
Does each oscillator on the string have a unique frequency?
No, that's not. And in fact, this is a good question, and I should have said that. Thanks. That's a good catch. So when I wrote down this, right, you have that for each n, for each frequencies, you have an annihilation and a creation. But each point can oscillate at different frequencies. In infinite mode, I mean, you just focus on this, you can oscillate with frequency 1, 2, 3, 4, and for each value of n, you have the relative, creation, and annihilation operators.
Right, so we've got, each oscillator
So
has,
each oscillate in...
Each frequency of each oscillator has its own set of creation.
Exactly, right, something like that, yeah. I saw her, yeah. I don't know who is the...
Sorry, just on the creation and annihilation operator. So you're putting energy into the string rather than
Yes.
creating a new string or getting.
No, you're not creating any string. You are basically putting energy. You are exciting a string, and so you are shaking it, and you are making the oscillator oscillate with higher frequency. Yeah.
Okay, so the picture I had in my mind, and I'm getting this from what other people have said, is that the way the string oscillates tells you what sort of particle properties you would have. So
Yeah,
this is really changing what sort of particle the string represents.
It's something like that. What I mean is that, the kind of particle that is produced, it depends on first, from the level of frequency. At excitation 1, you have a certain kind of particles. I'm thinking just one single harmonic oscillator now. Excitation 2, another kind of particle. We will see how the photon comes out.
Okay.
And yes, it's the dependence it depends on how much frequently they oscillate.
So can I just ask maybe this was just being blank. So when you first talked about the string, you were saying something like there's a harmonic oscillator at each point along the string.
City, yeah.
But here it looks like there's a harmonic oscillator for each frequency of the Fourier mode. For each frequency of oscillation, the way you are the Lagrangian and Hamiltonian. So are those both true somehow, or is it really that the?
So your second statement is there is a unique harmonic oscillator for. I'm sorry, say it again. The second part.
So it looks like the coefficient of each Fourier mode, when you write down the energy associated with it, it's treated as a harmonic oscillator.
Okay. No, it's not that an harmonic oscillator has just one frequency, because that's what it is implied from what you are saying. So you are saying that, like, this point has just n. Is that what you mean?
No.
For each point of the string, that point can oscillate with an infinite number of frequencies, let's say. N is a natural number, okay? And
But xm isn't an index for points, it's an index for coefficients of Fourier decompositions. Right?
yes, but okay, look here. So if you fix, okay, I got your point, hopefully. Sigma, right, is the point which we said sigma is here. You fix sigma, and here you have sigma x at 0, right? Single point on the continuous, okay?
Yeah.
Okay. Now rewrite this like this. I'm using Xn now. Is that okay? You now fix the sigma dependence, but for each sigma you have an infinite possibility to make this sigma oscillate, infinite number of frequencies.
Sure.
So this is the idea. So even it's not that if I fix sigma, I am also fixing an n here.
No, of course, no, I understand.
Yeah.
I understand
Okay,
the
so I
source.
understand.
I'm just confused about what things are being treated like harmonic oscillators. And the way you initially said it, I thought each point on the string was treated like a harmonic oscillator. But
Yeah,
then
that
the way
was-
you wrote
yeah.
the Lagrangian and Hamiltonian, it's in terms of the Fourier coefficients.
Yeah. Yeah, because the Fourier coefficient, they become the oscillation modes of the string,
Is there a sigma dependence in?
which is now in operators language, is this.
Yeah, I'm just asking before we get to operators, but.
Okay,
maybe-
No,
Other people are.
no, I'm sorry, I'm not getting your question. Well, it's true that we can also still talk later, but yeah, no, if you think this is crucial for understanding what I'm doing, just stop me and we will take some extra time.
No, no, it's-
No, but have you got the point? I mean, I don't know if I misunderstood. Maybe you are finding some kind of inconsistency in the way in which I wrote down here.
no, it's just from
I
what
think
it's
there's two ways to view it. Like on the one hand, you can view every point as a harmonic oscillator, but you can also view the whole string. And then, I mean, for the whole string, at each time there is a certain frequency, and this changes in time, right?
Right, it's a chain. And so
That's
even
a
if you
different view.
even if you took a point on the string, which is what I'm doing here, right? I'm fixing. This is a point over the string. Well, it's not this function. This is x sigma 0. You still have that this sigma now, there is no dependence on sigma, but still there is dependence on time and on n.
I think all that's going on is that the two views you're talking about are Fourier transforms of one another.
Okay, so we can write the Hamiltonian in terms of harmonic oscillators for each point or
Right.
for each.
Terms of
Right.
sigma.
That's right.
That's
That's
right.
right.
That's
That's right.
Yeah, that's
That's right.
Okay, so
That's right.
is that okay?
Yeah,
Okay. All right. So where I was? Okay. So yes. Before I start to, I need to say something. So let's see what I can keep here for later. I don't have to rewrite. Well, let's do this. We can get rid of this. We know now these are now operators acting on the states. We can leave this. Erase all this stuff. Okay. So we have a bidimensional, non-relativistic representation of the oscillation mode of the strings. I want to say something before talking about finding a photon, because the way in which we recognize that that particle is a photon depends on the spin state that we will be able, to read in this spectrum. Of course, things are much more complicated than that, okay? Spin is not enough. In a real class of string theory, nobody will tell you that. But in order to speak about other criteria to identify that is a photon, for example, how it coupled with an electromagnetic field and other stuff, I would need more machinery, and I have no time, right? I have until 12. Maybe I have some extra minutes, but not some extra hours or days. Okay? And so, let me say something about spin. This will be nice. So, let's think, okay, so let's think to massive particles, right? And massless particles. Where is it? I have massless particles, you know. You must and a massive particle is a particle that it's a mass. It has a mass. It can go speed like light. It cannot travel to the speed of light. Okay? So particles have spin, right? The spin is the way in which the rotation around the direction of motion. And so let's assume that there is a massive particle going this direction and spinning. What I want to say is that the notion of helicity, if this is the right word, it's not Lorentz invariant if you have a massive particle. Maybe you already know that. So tell me if that sounds, useful. For those who don't know, why it's not Lorentz invariant? Well, this is spinning like that, okay? center of the particle, and at my speed, and it is traveling to its speed, and I look the speed, oh look, this is clockwise, so this particle is right-handed, but the speed of the particle is finite, so I can, in principle, imagine that I can travel to its speed, right? And I can travel in a reference frame in which the particle is at rest. It's not moving, but still it is spinning. It doesn't change, right? I'm now in another reference frame. It is spinning, but I cannot see the motion because I am with respect. After a while, I get bored. Okay, it's spinning, and I start to play around. I start to say, okay, let's move at 45 degrees. Let's move to 90 degrees. Now the spin is perpendicular. Okay. And now let's go faster than this particle. And whatever before seemed to me clockwise, I said, I don't remember, right-handed, now is left-handed, right? Because I'm now traveling faster. Okay, so here I have three options. It's not Lorentz invariant, and this is the reason, let's say, it's not really, I mean, if you take serious textbooks, they will give you much better description. I think Zwieback gives something description. If a massive particle and spin j, the spin states is 2j plus 1. So spin 1, 3 states, spin 2, 5 states. But what about a massless particle? Massless particle, they go to the speed of light, and I have not this choice, I have not this choice, I have only this, right? So I can say, well, no, I can have this or the other one. It depends on where the particle is moving. So about the massless particle, I can say it is either left-handed or right-handed. So for massless particle, this helicity is a Lorentz invariant. Okay? It's Lorentz invariant because I have just the chance to go faster. I mean, not at the same. I mean, I can just move at the speed lesser than light. At least so far. Okay, so for massless particle, I just have two states of spins. Massless. And so the photon has just +1 and -1, right? We said if spin is 2, for a massive we have -2, right? -1, just let's refresh memories, right? 0, 1, +1, and 2. Yes, +2. 1, 2, 3, 4, 5. Okay. Now, that's what I want to say about spin. Okay. Let's see. We said these are decomposed in, these two guys are decomposed in annihilation and creation, so the only way in which the easiest way, right, in which we can see how observable act on spin, energy act on spin is through annihilation. So ground state of the spring. Ground state of the spin, the spring, sorry, spin, spring, string, I'm so sorry. Okay, let's say that when I say spring, I mean string. Okay? When I say, well, you figure out that it cannot be spin, right? I hope, right?
Yes.
Me, because unless I've been very confusing so far, is that okay? Okay, so if I want the ground state of the string, I will use the annihilation. Perfect. Apply to 0, and remember, these come from X. That's the X component, that is the Y component. Okay, they are acting on the vector 0, so they kill it, right? Yes. 0, 0. Ground state of the string. But it is important. This is something that you can find in tons of text. The ground state of string is not a vacuum state. It's not empty space. It's like if you have an harmonic oscillator sitting there doing nothing, unexcited, waiting. And so, basically, this is a quantum theory, uncertainty principle, fluctuation. There is something going on, like up there, right? There is still some tiny fraction of energy, despite it's like if you cannot get rid of strings even at the ground state. There is still something there, an energy, and therefore mass. minimal, tiny, but still there is an harmonic oscillator unexcited. So let's call the way in which usually they do is, let's call the state of energy of the ground state this, M0, right? To say this is the mass of the ground state.
Should remove your square.
I'm
You're
sorry.
always writing M squared, you should remove the square.
Well, yeah, I should remove, but you know what? Since we are thinking to this model, and since we said in the infinite momentum reference frame, you equate the energy to the square of the mass, and you can get this from the relation. We are still in this system, so I'm still this string is moving very
The
high.
units are correct?
I'm sorry.
The units are correct?
See it on.
Well, units, let's try to not to be too specific on units.
Well,
because
energy is
you would
mc squared, right? But
yeah, no, I'm saying, okay, okay, let me repeat this, that probably I've been not enough clear. So, when you are in a reference frame like this, and you will find a wonderful explanation in Sassari video, lecture 3, 4, I don't remember which one, but, and also Zwiebel, I can show you later. So when you are in a representation like that, the energy of the mass, in this case, can be expressed like the square of the mass. Because it comes from, as I said before, Sassagin shows in one of his lectures that you take this to be very, very big, you bring out of the square root, and then you start to manipulate with a Taylor extension, and then you will end up to say that E can be treated like the square of the mass. I know you're thinking to MS square, but this is a way, maybe Sassagin found this way of representing. I don't know if he was the first person who introduced that, because I remember that also I read something that he wrote. Yeah, he was here.
because you would think if momentum is big, that E is going to be proportional to the momentum. So
If the momentum is very big, the Z component of the momentum here. Yeah, but okay, I want to convince you. No, let me, you have this, look. Right? This is very, very big. Now these two other guys. So there is a way to isolate this guy from the rest and to bring on the other side. This won't change anything about the energy because, you know, I mean, in physics what it really counts is the difference between two levels of energy, right? And so you will end up with something like that. But yeah, I mean, I have to tell you, trust me. But I mean, I may be completely wrong. I completely misunderstood what I've been reading so far, and maybe Sasakin, when we watch this video, will be angry. What she's talking? Why she's? This is how I think. I mean, this is how I think he does a very nice presentation about. This is very basic algebra, but.
okay.
No.
Let me go on. So if P is much bigger than M,
yeah, you can.
you would say that P is going to surprise it. M is going to be negligible compared to.
Yeah, but you can separate and divide it for PZ, then you can bring here, then you can do some other manipulation that, and then you get just, well, it's, you have to take the square on this side, then you bring this here. I show you, promise.
Okay.
Yeah, no, because otherwise, no, you know why? It's not because I don't want to go through this, it's just that I'm afraid that it's 11. Yeah, that's, but we can have lunch later, right? Can we? Start lunch later, stay more. No, I'm joking. Now, you are scared. I'm not going to delay the lunch. I'll finish in time. So.
It's okay.
Okay. So let's back up. This is the mass of the ground state, okay? And, all right, so we said there is something there is a mass. So what we should do, we said everything about the string. Now let's take the excitation of one. Now I have an excitation I'm using here the reaction operator, X component. What can I say about these two guys? These two guys apply to 0, produce, can I erase this? I think you have all the notes, right? I mean, that's And then if I need, I will use it. I will write down again. Okay. Master state, I can, well, this is clear. I repeated this once a time. So these are two states. And the energy of these two states now is, if that is what, there was m0, it's m0 plus 1, because it is, I am adding 1 unit on the x component, and I am adding the 1 unit of energy along the y component. So what can I say about these two? Well, they are two vectors, right? Let's remember where they come from. They come from one from x, like 1. They are two vectors. This is an operator applied to vectors, and it gives another vector, like operator, okay, all the time. And they are relative to the same eigenvalue, I mean the same energy value. So if I take a linear combination of these two, I will get another vector which refers to the same energy value. This is how, I mean, the energy value is the eigenvalue, right, of the operator energy. So when you have it's linear algebra, right? So you take two vectors inside the same eigenspace, which is a subspace. You combine them linearly, and you will get another vector in the same eigenspace, right? Okay, so I want you, what else can I do with these two vectors? Well, think to something like that. Have you never heard about polarization of light? How many have heard about polarization of light? 1, 2, 3. Oh, good. So the polarization of light, for those who didn't raise their hand, is the direction along which, wait, let's do it. The photon traveling around z, my favorite, right? Z. The polarization of light is basically the direction along which the vector field is fluctuating, right? And when I say polarization of photon, I'm saying it is the quantum version of polarization of light. So when you have an electron going like that, right, let's say this is x again, and this is y, I keep repeating the same notation, you will have the electric field, of course, the electric field is orthogonal to the direction of motion. But you can have, let's say, it can be orthogonal in this way or in this way, right? So let's call this the vertical component of the electric field, and let's assume that this is the horizontal component of the electric field. In case these are two extremes, right? You can have vertical electric field. Of course, what is vertical and horizontal? Horizontal, it depends on choice. You can switch the other way around. So basically, any other polarization of a photon is a linear combination of these two. So something that comes out here from the black hole. But if it is a linear polarization, you know that that vector will be on the vector which comes out will never change plane along zeta. It will always belong to the same plane, because I can imagine a plane coming out. If it is circular, it will be like the polarization comes out this plane along zeta, and then we will change plane, and it will comes out in this way. Okay? So I have two ways of writing linear alpha beta of horizontal, alpha beta belonging to real number, and then I can write alpha e vertical plus IB IB in horizontal, and here again alpha b belong to R, but I introduce I, which means it's a circular polarization, right? It's the complex plane. Okay, I want to show you that these two guys behave pretty much like the polarization of photons. And then I want to say something, yeah, about the spin. So they can be, alpha plus beta. Sorry, I knew that in 10 minutes I would have messed up, plus and minus and everything, but let's say plus 1 applied to 0, they can be linearly combined, and they can be circularly combined. to their definition, their vectors means after all, you know all the things circularly. So they can rotate right on each other like these two guys do. They're doing, they can do this all the time. The rotation is rigid, and okay, so they can rotate, they can be linearly combined, they can be circularly combined. There is, the spin is 2. I have 2 states, A and B. It looks like they are, in some sense, a massless particle, and these are the 2 things that I'm saying. I should say much more. Let's say, I'm aware that I might sound very sloppy now to all of you who already know these things. Let me think that this is a photon here. These are 2 state of polarization of a photon. I need more things, but let's pretend we don't need more things, right? So far, so good?
Wait, the photon is massless, so...
Yeah. Sorry. Yeah, the photon is massless. So it has, photon has a spin 1, right?
Mm-hmm.
So here we have 2 spin states. Massless particle can just have 2 spin states.
I thought you were increasing the energy by applying...
I increased the energy because I wanted to get a photon.
Okay.
Because if I was stuck here, you could have waited for the rest of your life, no photon would come out. You need to take A1. You need to increase the frequency of your harmonic oscillator of +1 unit. So you get your photon. So I'm saying, well, it's like an investigation, right? Okay, I have this element. They behave very nicely like the polarization of light. Also, they have 2 spin states. So, this is a massless particle, according to what we saw. So this is a photon. And now I have a slightly problem, and now I want you. I'm sure you will realize what I'm talking about. And this is the problem for which, one of the reasons for which extra dimensions were so desperately needed in string theory, in the quantization of string theory. Not the only one. We are going to see something more serious. 10 minutes, maybe 10 seconds.
Can I ask a quick question? I'm sorry.
Yeah, sure. No.
But just to follow up on what Manas was saying is, it sounds like we should, when you add the energy to create this state, we should not think of the relationship E equals m squared applying here, that we should think of the energy as some, I mean, the photon has energy, but we're not relating it back to mass, because the photon is massless.
Yeah, it's true.
It's just the interpretation of it is different here.
Yeah, no, it's true. Okay, I'm saying that the energy is m ground state +1, but this will correspond to some big m squared, which is the mass of the photon produced at that level. Okay, this is the mass of the ground state.
Yeah.
I added an energy unit,
Yeah.
and so I have m0 +1.
Right.
That is the energy. I should call, let's call this energy 1.
No, I understand.
Let's believe in 1. But this energy is, sorry, I interrupt you. Still follow this rule. And in fact, this E to the level 1 is equal to the mass square of the particle, which is produced.
I think what Saman is asking is how he's supposed to understand in this context the locution that the photon is massless.
In fact, I'm going to say right now what is the problem here. Because the problem is I'm still applying the notion, right? I'm saying, well, there is energy, the energy level is this one. So there is a mass, which is the square. But wait a minute, photons are massless. Okay, so what I can write is 0 equal to +1, which is the element. And now we are in trouble, right? Everybody can see, right? I'm testing you. Can you see that? This is 10-second test. Can you see why? Okay, I trust. M0 squared. We are saying that the ground state, there is a mass of negative particles, the targets, the guys that nobody wants to have in a theory. So Okay, I want to be very, very concise, but this is the reason for which we need extra dimension. If I started this quantization using a d-dimensional space, it would have been helpful some of you because I've then introduced a lot of more machinery like Lazaro algebra, computation relation, it would be a bunch of symbols. But at a certain point, I would have reached a stage in which the mathematical formalism would tell me, okay, now you have to pick a dimension here. And I should have picked t equal to 26 in the bosonic strings, and definitely different from 3. Okay, so the fact that I was quantizing in three-dimensional has created this problem. A change of dimension will get rid of the tachyon, still will keep the photon at level of energy 1. So that's a thing, right? We want photons. So okay. Let's remember, okay, let's move to the gravitons now. And so we can, we are in a good shape. Can I erase this? It's not important, everybody knows about it. Okay. Alright, so I want to keep this picture again. We need, what else we need here? Well, let's keep in mind this. So we saw this problem. Gravitons, well, they come out, well, they are related to oscillation of closed string. So, but I mean, it's with closed string, these are like this, right? Let me write. This is a closed string now. This is 5, this is 3. And let's see that there is an increasing directionality of sigma. Okay, this is how sigma. So, I would like, maybe this is not really useful, maybe, but let's say that when I write down what I just erased, I think I didn't have to erase, but let's say that the x sigma and the y sigma looks a bit different. And I can write for you here very quickly. In the meanwhile, think a bit about, x sigma. And maybe if I write this one, now we have it's a, I don't want to make a sign mistake, and in order to create maybe a discussion which are just connected to, x minus 1 minus n now, and sigma plus center of mass. And here it's pretty much the same. Again, I will stick to the same convention. Well, n minus, I will use it's n, a, and sigma, right? And plus still n bigger than 0, and then we will go to n, a, minus b, and sigma, q, sorry if sometimes I will see some tiny more q and plus. Okay, you see, I have minus, so what I have to think about the closed string is the following. So, they basically, when you excite a string, if the string is closed, you will have a right moving excitation and a left moving excitation. Something like a wave, right moving wave and a left moving wave. Minus n for the guy left moving, plus n for the guy's right moving. Okay, keep in mind that I should be very careful. I'm saying left, right. This orientation has nothing to do with orientation in space. The orientation of left moving and right moving has to do with the directionality of increasing of sigma. So let's find a convention here, because I'm afraid that in 5 minutes it will be a mess, because I will use left polarized in the case of photons, and let's say that when it is right moving is clockwise. Does it help? When I say left moving is anti-clockwise. But keep in mind that if I by mistake I will use left moving, which is the way we define in the textbook, right? But don't get confused with the left-handed spinning of the particle, because that is an orientation in space, x, y, z. This is an orientation intrinsic to the string. Intrinsic, there's nothing to do with the space around. Okay, but that's just, interesting, right? So you will read, if you will read in the future, this is kind of, I want to give you a guideline to orient yourself. Okay. So, what should we say about this? Let's talk about creation. So we have, at this point, everything is double. You will have this, the one which has so I'm not detracting energy. Okay? I am adding energy to the left. I am adding energy to the right. And they always go together, always. The same for B. And then annihilation. Okay, I'll show you very quickly that you can't combine this guy as you want. Okay, there is a condition which is called the level matching. It's intrinsic in string theory. It comes from, I'm not going to prove the level matching rule, but it comes from something about conservation of energy, Naylor theorems, and has to do also with the charge. String carries charge if they have the direction of if they are oriented. Some of them are not oriented, but we were just thinking of oriented strings. So all the possible combinations are the one I'm going to write here. Where is it? Okay, it is there. Maybe I should just keep there so I don't have to do it back and forward. Okay, this is the only the allowed combination, let's say at level 1, okay? So this is much easier. And then we will write down exactly how the graviton looks like. What is a graviton? And okay, this is allowed. A, now we have AB plus 1, this minus 1, and then we have B plus minus 1, B1 plus. And let's not think we want to create a graviton, so we don't care about it. These are, well, there are also other allows combination if I'm not wrong, but let's consider this one. No, wait a minute. No, for creation operator, these are the only possible combination. Of course, at level 1, at frequency 1, okay, in general, you cannot have something like that. For example, if you are doing closed strings, you see that, right? Because if I add something on the right, I have to add something on the right, the left. And so I needed a minus 2. Okay, so this is how, combining all these guys, what you will get is something like that. Let's look at this. Should I? Okay. Let's say we get this one. I'm sorry that I'm giving to you this list, but the only fast way I can do this is just taking them from my notes and skipping all the passages, or not mix the plus with minus with 1. And this is the second case. Plus 1. I promise it's going to become much more exciting, okay? In 10 minutes. Minus 1, minus 5, B plus minus 1. Okay. There are other two combinations. We don't care now. Do you recognize this guy? So, we said that those are photons, and we said gravitons are photons coupled. This is something very not going to give any kind of physical argument that you can find everywhere. Maybe you can't, maybe later on we can discuss about that, but right now I'm really anxious to reach what I want to reach, which is the main point of this presentation, but that main point really needed this. So, you see, they are two in couple. There are two photons in couple. So, and they are basically, we said they have spin 1, so here I have a couple of right clockwise, circularly polarized photons traveling together. 1, 1, so they spin amounts to 2, right? And here we have a couple of photons, anti-clockwise, circularly polarized, adding to -2. And so this is how the photon looks like for a string. Okay, this is how, this is how graviton looks like. I can get other two combination with spin 0, and that should amount, there should be something like the dilaton, another kind of particle predicted by string theory, and another one which I don't remember the name, so yeah, I can't remember now. So 2, 0. Actually, yeah, well, I mean, when you do this, when you do your computation by yourself, you get these 4 states. You say, hey, what particle is this, right? Because if it is massless, cannot have 4 states. If it is massive, if it is spin 2, I have 5 states. If it is spin 1, I have 3 states. So what is this? And then you realize, oh, these are 3 particles. 1 spin 2, and 2 spin 0. Okay. Good. I'm glad that I reached, yes.
So the graviton is massless, right?
The graviton is, yes, it's a massless,
Yeah.
yes.
So how can I understand the coupling of two photons? Because in electromagnetism, the
It's not
is it
exact-
like adding?
yeah.
So it, yeah.
Yeah, no, I understand what you mean. And that's,
Logarithms.
you know, this is, as I said earlier on, right? I cannot give you, actually this stuff about spins, it's not really the old story. You don't identify the nature of this particle just to look into the spin. You identify the nature of this particle, also how they couple with the electromagnetic field, how two photons. And so I'm now unable to give you this answer because I would need to introduce more machinery, and that would bring me to be unable to arrive to emergence, which is there waiting.
But it's not true that the graviton consists of two photons.
Well, it's an approximate. I mean, you can think to a graviton like two photons going, traveling together with spin 1, 1 that amounts to angular momentum 2, and spin or spin minus 1. So your question is how these photons interact with each other or something?
Yeah, maybe the question is, if we take that literally,
Yeah.
then is there a physical process or an experiment that could cause that to break up into two photons? You know, or is it just a mathematical construct, and
This is
the
a-
graviton is stable and doesn't break? You know, there's no
Yeah,
chance.
no, there is a mathematical construct that, this is the language of string theory. This is a mathematical representation of what a photon looks like, what a graviton is for string theory, how you can read it in the spectrum, but there is definitely some other physical literature about the physical dynamics going on there, yeah. Yeah.
But I guess the question that's floating around is something like, even if we can't here go into how we see how they couple to various other fields, are you saying that it's going to be a property of a pair of photons like this, that they're going to couple to the stress energy tensor the way the graviton does?
Okay, let's say this.
And you know, the question is,
Okay.
how could that possibly happen?
Okay,
Photons don't have couplings, anything like that.
let me say that. Maybe I can. You know that gravitons, every string theory has gravitons. If you start with, I mean, a photon is an open string theory. Okay, now I'm saying particles are string. A photon is a state of excitation of open string theory. Maybe I can answer to this question putting something on the carpet, but trying to give you a more mathematical representation. Even if you start with an open string theory, you will always end up with having closed string theory there. Always. What I mean is that graviton comes from a closed string theory. So let's see this in a kind of pictorial way. How do two open string theory can couple? I mean, there is a probability amplitude that regulates the fact that they will join at a certain point. And In cases like that, it's very high. In the sense that, let's say you have two starting points and you have two open string theory, they are both direct. So it's highly probable that a certain point they will join in a way like that. They will become a unique open string theory with this directionality. Okay? So they are bringing charge. Open string theory carry charge, which is a generalization of the electromagnetic field charge. But then there is also a very strong probability amplitude that this guy at a certain point, the tail, will conjunct with the tail, with the head will join the tail, and you will produce a closed string. If you read this on spectrum at energy n equal to 1, you can have a mathematical string representation. It's not even mathematical, but it's a pictorial pictorial idea of how much probable is the two open strings can combine and create a closed string. So, I don't know if I'm answering to your question.
I mean, here's the sort of question, maybe this is just too much to answer. So one hears this slogan, one hears the slogan all over the place. Look, one of the great triumphs of string theory is that it predicts the existence of the graviton.
Yeah, it must predict.
Right. Now, I think what the questioners are asking is, how are we exactly supposed to take that? Are we supposed to take that it predicts the existence of a spin 2 particle in the way you just described, or more particularly that it predicts the existence of a spin 2 particle that couples in a particular way to the stress energy tensor, okay, in the way the graviton does.
Okay.
If it's just the first, then the achievement doesn't seem that impressive, okay?
Yeah.
If it's the second, then we're really getting somewhere. But so far
No,
it seems like you just made the
second-
first one plausible.
I mean, how do you know this is the graviton? How do you mean?
Yeah, but the same. You could have asked me the same there. How do you know that is a photon?
Yeah, sure.
And my
Sure,
answer,
sure.
because I didn't give you enough. I mean,
Absolutely
I
right.
didn't give you
Yeah.
enough physics.
Right,
I didn't tell you
right.
anything about that
Yeah.
guy coupled with an electromagnetic field,
Right.
So, and still I have to be inside this constraint and say, okay, let's pretend there are no other things to think about. Yeah, you're right. How do you know that this is a graviton? I gave you very minimal pictorial description, or
So
what I have
maybe
been
here's-
doing is, what I've been doing is, okay, let's look the spin. Spin is 2, it's a massless particle, but yeah, it would be very complicated now too, but it's the second one, yeah.
Well,
I
but
think it's
so
the
here's
second.
the question.
Yeah.
We understand you don't have time to show us this here.
Yeah.
Are there in fact, arguments with some degree of compellingness in this formalism that not only will get the spins of these particles out of various excitations of
Yeah.
the strings, but we're going to get the right kinds of couplings out?
Yeah, yes. If
Okay.
you, I mean,
Yeah.
my impression is that something very basic is in Zwiebach I wrote down, BBS I wrote down, and I'm not sure whether Sasakin in what he, well, he also wrote tons of books about that. So these are my 3 basic references. There are other references I have in mind, but yeah, I'm pretty sure that there is an exhaustive analysis.
We will take it on faith.
Yeah, you have to trust me, right?
Yeah, no, we do.
Definitely. Okay, so I guess, okay, Emergence, finally. I have another, no, it's 11:30.
Yeah.
Oh no, this is horrible. Okay, just 10 minutes more.
No, you have a half an hour more.
Okay, wait a minute. I have an half an hour.
You don't.
At least.
Can I have 40 minutes?
Yeah, sure.
Oh, yeah. Go ahead.
45?
Yes.
Should we skip lunch?
I'm gonna stay here.
Thank you. You will be the only one, everybody.
It's okay.
But then you will pretend to the other what I did. Okay, should I do this? Yes, let's read. Okay, now let's get rid of this. have all this stuff. I don't know if you really, probably you are wondering, yeah, but what about emergence? What the hell? What's the connection here? Why is she doing this? This is just a very basic introduction to string theory, right? Okay. Emergence. Let me say something, few things, okay? This idea of emergent space-time string theory, during the first period I started to read the literature, scientific and philosophical, I got very confused. Fantastic physicists writing about that, very great people who know these things very well, but what I found was that this notion of emergence of space-time very often has been used in different ways, in different contexts, but this way of, I would say, in different contexts, but meaning the same, I should say more correctly. And people just use the notion of emergence in a way that overlaps. And it's not clear. I think we should distinguish two notions of emergence, okay? What I'm going to present here more extensively is the notion of emergence of ordinary space-time, which should keep distinguished by the emergence of space-time required by string theory, which are the higher dimensional space-time. And the reason for which this is not just a purely semantic distinction, just purely things. The reason for which I point out this, I want to make your life easier, okay, when you read this stuff, if you will be interested. The reason is that the two notions, the analysis of the two notions are rather through different methodologies. The first one, the one which is we are going to see, is basically a mathematical derivation from some mathematical features in theory of what it is, what the vacuum, the solution to the vacuum Einstein field equation, which is the ordinary space-time. That's what I call the ordinary space-time, the four-dimensional solution to the vacuum equation. And this requires mathematical derivation that we are going to see. For the other emergence, so basically it's an intertheoretical relation, right? So I want to show you how general relativity emerges. I'm taking this notion of emergence now in an unproblematic way, okay, from string theory. But when I talk about emergence of higher dimensional space-time required by string theory, basically the solution to the vacuum equation of motional strings, right? I need to use arguments which use the notion of duality, what I mentioned earlier on. And my point is that we can think about emergence in the first case. I'm not so sure we can talk about emergence in the second case. About this second case, if we will have time, I reached basically a conclusion which is very similar to a very interesting paper I read. He reached the same conclusion about the ADS-CF correspondence, which I don't think is a case of emergence, like many people say the emergent quantum gravity and so on. But we have the same conclusion, but his name is Nicholas Teck. But I think this is the way in which it should be written. I don't remember. I apologize to Nicholas if that is my right last name. But he used a completely different argument. Okay? So I'm going to use a completely different argument, but for some reason, which I think is very nice, we reach the same conclusion. But okay, let's start now. Okay. So far, I need to give you these two ideas, okay, that I will keep in a box here. And definition of Weyl transformation. This will be important. Do you know what Weyl transformation is? How many people? Good. The only one? You want to come here for this? No. I'm my students in Chicago, so they hate me. So.
This is one of my favorite things in mathematical physics, so this is...
Okay, cool.
Exactly.
Okay.
Definitely.
So in pi transformation and also conformal transformation, I should say. Let's put, let's say here, conformal transformation, but let me say what I mean. Okay, some people, they treat conformal transformation like if they are value transformation. Some other say conformal transformation is something more. I am in the second group, okay? So conformal transformation is basically diffeomorphism, a change of coordinates, diffeomorphic change of coordinates among points. But and this is one aspect. Also, it is a bisymmetry, but it's a Weyl transformation. But careful, Weyl transformation do not act on coordinates; they act on metric tensors. They take the metric tensor, they stretch and contract lengths. But so conformal invariance usually invariance by diffeomorphism, transformation of coordinates, invariance by rescaling of the metric. Okay, by transformation, I want to give you a definition. Let's call it omega. And so you have a metric, which I want to call this to prepare the next thing here. This is a metric. And I just bring this metric and rescale with a factor, let's say 2. There is a 2, some people have 2. Some other no. Where sigma, at the moment, let's say it's the variable over the manifold, on which I am, sigma is the variable over the manifold, on which I am stretching this tensor, okay? Let's say this, that in general, if for dimension d, a way to look omega depends on sigma, but there is a very, very common. So in dimension d, okay, I can rewrite this transformation in a way which is the most commonly used. And so this is, I still have p, but the scaling factor here has this structure. P minus 2, which multiply omega. Omega now is constant in k and d. And you can see now, just look to this. This is the general one. Just look to this one. And so we have two cases. If b is equal to 2, conformal valid invariance. Okay? By invariance. If d is equal to bigger than 2, I want to define for you the notion of infinitesimal conformal transformation. And this is absolutely will be so important for what we want to define. So what does it mean, infinitesimal conformal transformation? It means that I am on my manifold, right, of dimension bigger than 2, and I take this manifold and I just make an infinitesimal stretching or relating. And this is how it works. And you can figure out very easy why it works like that. You basically take the derivative with respect to omega of this stuff, and you get an infinitesimal conformal transformation. Okay, let's keep this in mind for the future. Now, we said, let's get the general relativity out of string theory. Let's start writing classical action of string theory, the so-called very famous sigma model, sorry. I'm going to introduce you to all the guys I'm writing down on the blackboard. I know that some of you already know, right? But for those, just to have an idea. So this is an integral over sigma with sigma, well, we'll see. This is my auxiliary relative. Okay, I write faster if I don't speak too much, so let me write first. Oh, sorry. Oh, sorry, this dependent sigma, this dependent sigma. Is this clear how am I writing? This dependent x. Let's see if I do it here. So this is a derivative, okay? This is another derivative. Okay, Okay, so what do I have here? This is the Riemann surface. It's the worldsheet. The integral is done on the Riemann surface. So it's a two-dimensional, it's two square. Okay, here, change of terminology. This sigma is basically now tau and our old sigma. If you prefer sigma 0, sigma 1, where sigma 1 is the old guy. Let me see, it's sigma, do you remember? Right? This is sigma 1, okay? Is that confusing you? But okay, I just want to keep using sigma. It's much nicer. This is a tau and sigma. These are parameters over the surface. Okay. Now, look here, this guy here, it's just our familiar, where sigma now is 2. It's what we wrote down here, right? It's sigma. I wrote down in a different way. In that case, there were coordinates of space-time, depending of the point over the string. Now, I'm thinking to these guys like fields over the string. And this is the part I prefer. Identifying this guy. This is really, really cool. This is any Riemannian geometry. Any possible thing to the family of all the Riemannian manifolds that you can have, okay? An arbitrary Riemannian I hope I got the right number of them. Riemannian, is that right? Yeah, well, okay. And this is a classical action. Okay? So you see the classical action can be formulated with any Riemannian metric of the target spacetime. Okay? Look, okay, very careful. The integral is not the spacetime. The integral is over the worldsheet. Okay? And these are, as usually you do in quantum field theories, then you have a target spacetime over which you project what's going on. These are fields. Okay? Gamma, I didn't say what gamma is. Do you know what gamma is? It's the intrinsic metric of the worldsheet. It's the string metric. Whether or not we should say metric, it's another issue, philosophical, mathematical, everything, but it's not the issue of this talk. We can talk in another summer school. Okay, so what should I do with this? Maybe I should just tell you what I want to do.
So gamma is the metric on the worldsheet, and the G is the and G is the metric on the target space.
Right. G is basically any Riemannian metric on the target space. And okay, a tip, a suggestion. Whenever you read, I'm sorry, my handwriting is. Whenever you read A and B, it is referred to the metric of the worldsheet, the auxiliary metric. When you read mu, it is referred to the target space.
But why did you define the Wild transformation on the worldsheet and not on the target space?
Because the worldsheet of the string is Weyl-invariant. And I defined the Weyl transformation over the worldsheet because you notice that I'm using gamma, right? The same metric, yes.
In target space isn't Weyl-invariant.
You don't have a conformal invariance. I mean, I recently read something about the fact that it has been argued about the fact that general relativity has more degree of freedom in choosing metrics, and that sometimes metrics in the same conformal class, equivalent class, they are treated equally, but this is just an argument that I didn't read the paper, I have to go through. But let's say that when I speak now of Weyl invariance, I'm talking to the metric of the worldsheet. The very nice things about that is that over the worldsheet, whatever you do to your length, so you stretch, you dilate, you rescale, this has no physical meaning. Okay?
So just a remark, what do you mean by general relativity is Weyl invariance? You just take a
No, I don't mean general relativities.
No, I'm conformal, yes, conformal invariant. I mean, you can take a two-field scalar tensor theory, and you can just define conformal transformation which projects you this theory onto classical general relativity. So this is easy. We take a ghost and a normal field, so phi squared minus s squared, couple non-linear to gravity, and define it such that so your transformation gives you in one reference the classical general relativity, so it works.
Okay, so you,
I can show you it.
okay, now that's good. So you know the argument.
Yes.
I mean, I read
No,
that
it's
as,
mathematically extremely clear. So.
oh, okay.
Yes.
So I read the fact that it's not clear, but yeah, but some people don't think the argument works. I read, but some other people think they work.
So
You
it's
are.
a very special scalar tensor theory, and as you know, all scalar tensor theories are very invariant, and you can find them.
Okay, that's cool. So we can talk about later. Yeah, so that's cool. So we're now thinking about this kind of invariance. So what do I want to do with classical action? Why people just don't start to, well, maybe you don't start to throw tomatoes against the blackboard, because you see someone could get very upset that there is a metric here. You're talking about emergence of space-time, or what do? You write down an action which has a metric in it. Yes, I mean, but look very careful. I mean, some people could think, oh, you want to show that ordinary space-time emerges, so what you usually should do is start with some mathematical structure, and I think we had a conversation with David, and David was not the only person who asked me this. You start with a mathematical structure with no metric whatsoever, Riemannian, non-Riemannian, or whatever, and then you get something with the space-time metric. It doesn't work like that. It's a bit more tricky, but the basic stuff is keep in mind that a classical string theory works on any Riemannian metric, okay, generic. Okay, so what I want to do is this. I want to quantize this action, and I will quantize this action not with the canonical quantization I used earlier on, but I want to quantize with the method of the quantum loop correction, and we will stop already to the one loop correction, the final method. So you start basically to perturbate this action with quantum fields around. And what I want to show is that the quantization of this action will produce a quantum string theory, but in order to have a consistent quantum string theory, there is a condition. Okay? In order to keep the conformal invariance, because this is the problem, when I will quantize with this quantum fluctuation, at a certain point, I will introduce a control term, and this control term in the perturbation of the action will break the conformal invariance. But I want to keep the conformal invariance. Who doesn't? I mean, I start with a classical action which is conformal invariant, and I want my quantum action doesn't lose any of this symmetry. And so we can work in such a way on these control terms, which is the term with which I renormalize the quantization, in a way that I can find the solution to the vacuum Einstein field equation. And what I think is very impressive of this argument, of this theoretical argument, is that we will work for a while in a regime perturbative, and then out of the blue, it will come out by purely logical consistence, the Einstein field equation. Not the perturbative one, the exact one. And then I say, okay, this is what I mean for emergence of space-time string theory. And my suggestion for those of you who want to study these things in the future, go through this beautiful mathematics that gives you a very strong theoretical argument in combination to what I've been showing 10 minutes earlier on. We can talk about ordinary space-time emergence in a rigorous way, and once we have the math there, we can read this math and ask to ourselves, in which sense this is emergence? Because emergence is something that it has been used in the traditional philosophical tradition, beautiful philosophical tradition, in so many ways that we should think more carefully. Maybe it's something else, maybe we can reformulate the notion of emergence. Okay, so I want to quantize this now.
Tizi,
question.
Yeah.
Does the exactness of the space-time that emerges sort of caution us? Is that like a caution sign for how
I'm sorry, say that again?
realistic we should interpret or understand the emergence? The fact that the space-time that emerges isn't perturbative, does that take away from how realistic we should interpret it?
Well, yeah, let's say this. If you take, when you say realistic, you mean ontological emergence or something? Okay, this is a very good question. And I'm going to say something now, a few words. But then I will keep, So if you read this emergence in terms of ontological emergence, let's think to the way in which emergence in the philosophical tradition is taught, like ontological emergence is. Usually, I'm not saying everyone does that, usually people supporting that argument are relying on another assumption, that there are really distinct ontological levels of reality out there, right? And this has some kind of consequence. So when you say that the level of reality is ontologically higher, you are saying that basically some of the entity, physical properties, structure, nomological, whatever, living in that higher level are in some sense new ontologically with respect to the properties of the lower level. Of course, some of the properties at the higher level can be derived, but not everything, because that is an ontological emergence, right? So these entities, these physical properties, are in some sense irreducible, are in some sense not explainable in terms of the lower property. And this is something that is not going on here. Because the quantum string motion entirely explains general relativity. But I wanted to rescue notion of emergent, though, weaker. And we were going to see, so yeah, I don't know if I'm...
So, I mean, the point you're making there seems to be one about ways that one could understand the strength of the emergence relation itself, where we have in mind some sort of ontological understanding of emergence.
Yeah.
I was more sort of asking about the fact that what emerges, whether we have a weak or strong understanding of emergence, and it seems you're going for a weaker notion, that's perfectly fine.
Yeah.
I was asking whether or not the fact that what emerges in this weak sense is an exact space-time that's non-perturbative, does that suggest that what's going on here shouldn't be interpreted too realistically? Shouldn't be understood too realistically? In other words, should the string theorists be striving for some sort of argument that that gets you the weak emergence of a perturbative space-time?
When you say, when you say too realistic, you mean, let me see, too realistic, you mean, in sense of ontology, yeah. Well, okay, let's take a cautious, let's be cautious. Cautious is the right word. Let's take what we are talking, in other words, let's put it in this way. When I'm doing this when I'm studying this emergence, what I'm doing basically is studying the intertheoretical relation between string theory and general relativity. And when you mean a realistic, so basically with this string really realistic, you mean there are really string producing emergent spacetime? Is that what you mean, realistic? Do you have in mind some notion of causal power?
Of what?
Causal power?
No, not necessarily. I don't think that, this sort of like weak sense of emergence is necessarily causal. So maybe I could illustrate this, and then if the illustration doesn't help clarify the question, then I'll just drop it.
No, I think I got it.
So there are these theorems which try to establish that from particular properties of sort of freely propagating background radiation, particularly the isotropic properties of that radiation, you could infer that the space-time in which you're situated, in which that radiation is propagating, is perfectly Friedman, Lemaitre, Robertson, Walker. That's the structure of the space-time. And that is perfectly homogeneous. But there's a question as to whether or not we should understand that result really. I mean, our universe, our cosmos isn't perfectly homogeneous, right? And so there's a sense in which we should be cautious about, you know, understanding the results of this theorem realistically, right? So this adds a little bit to the flavor of what I mean by realistically. Right?
So not in the sense that
context,
it's not an idealization. You mean?
Yeah, it's this theorem looks to me as if it's going to be much more of an idealization that shouldn't be understood as something which in some sense corresponds to reality. And I'm asking whether or not, with respect to your argument about the weak emergence of space-time, since the space-time is perfectly exact, should I just be understanding this idealistically? I mean, what really are the consequences and implications for how we should understand the world, you know?
Okay.
In which we find it. That isn't.
Yeah.
Perfect.
Okay, let's see. You know, I think I want to modify a bit this notion of realistic, but let me say, I think the way in which you should understand is this. So, this is an intertheoretical relation. Okay, you get the Einstein field equation in exact way out of a perturbative regime. The quantum string of motion, this quantum theory, dictates the structure of the gravitational field with which the string couples at a classical level. And it tells you that that is the Einstein field equation. When I say that at a classical level, is that in some sense it is realistic, but it is still a description of reality in a much larger scale. So, realist. Yeah, I'm not denying. I mean, when I say a weak notion of emergence, I don't want to commit to myself to say, hey, there are no levels of reality out there.
Right,
I don't use an ontological notion, but I still think that there is something out there that we are describing inside the domain of application of this theory, and this is all we have to talk about reality, right? So if this is all we have to talk about reality, if the ontology of a theory is internally defined in the scientific theory, and because every theory has an ontological core, has a physical part, has a mathematical language, and there is an ontological theory which is a kind of domain of intersection of logic, math, right? What the theory tells about the world, and I don't see how we can go out of that description and look for some noumena, Kantian noumena out there, and try, so if for realistic, are you thinking to some distinction between phenomena and noumena or something? No, okay.
That's fine.
So sorry, David is keeping his.
Maybe this is, actually I'm not sure if this is what Chris had in mind or not. But here's something that might puzzle someone who hears, look, what pops out of string theory is exactly and non-perturbatively the Einstein equation.
Yes.
Think about the way we get thermodynamics out of statistical mechanics.
It's an approach.
Right.
You're talking about, so this is
different. And the feeling we get out, okay, isn't exactly thermodynamics, okay? The laws of thermodynamics turn out to be, strictly speaking, false, okay, when we derive them from statistical mechanics. There are fluctuations, blah, 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 and that's the kind of thing that we're very much in the mood to expect, okay?
But this is
when we derive a sort of higher level theory from a lower level theory.
Right.
It would be a surprise if statistical mechanics gave us exactly the first and second laws of
And you are going to be surprised. Because this is what is going on.
Yeah, I'm already surprised. Right? But here's what's puzzling. If the higher level theory turns out to be exact, okay, now maybe I don't know exactly what exact means, but if it turns out to be,
No, I'm just
be exact, What's the evidence that there is a theory beneath it?
Right.
That's what's going on in thermodynamics and statistical mechanics is, on closer experimental observation, we find that thermodynamics isn't exactly true. There are fluctuations, blah, blah, blah. That's sort of a clue to there being something going on under the table, okay?
But
If
here,
somebody
there is
says,
something going on.
If we got thermodynamics exactly out of statistical mechanics, there would be a legitimate question about why we believe in atoms at all, okay? Maybe we could get it this way, but there's nothing wrong with thermodynamics.
I'm sorry, I don't agree.
Okay, good.
Because see, we get the exact equation, right? The vacuum solution of the Einstein field equation.
Good.
In a way which is exact. So maybe this is what you're thinking about realism. I'm sorry, I didn't understand you very well. But it's not that, well, there is nothing on behind. Why should we keep in consideration these quantum theories if we have an exact? But the point is this. String theory, the quantization of string theory explains to you why ordinary space-time has the shape the metric which it has.
Yeah,
This
just
sense
like
is more
statistical
fundamental.
mechanics.
What I'm trying to say.
Yeah.
So you have an effective theory and a more fundamental theory.
Right.
Effective theory, let's say general relativity,
Right.
it tells you how things go.
Right.
In that domain of application, right? But it doesn't give you an answer to why things go like that. Why space-time is like such it is, space is that, geometry is gravity, and why space-time. I think Professor Klimak was projecting some slides, right, in which there was written, matter tells to space-time how to curve, and space-time tells matter how to move along the geodesic. And this is an symmetric interaction, but you don't find the answer in general relativity of why is that. String theory is telling you why is that. Because the string theory is putting constraint on the fact that when you have an effective description of a string coupling with a background gravitational field, the quantum string motion is telling you that the only possible gravitational field with which the string couples is the Einstein gravitational field. And plus the fact that we derived the quantum of that gravitational field from the spectrum of the closed string, opening a window on a much finer perspective. So when we think to strings interacting with background field at a classical level, what we should really think, what it is really going on there, revealed by the quantum motion underlying, is that the string theory is interacting with its own mode of oscillation.
No,
and that's for me, that means, what does it mean that ordinary space-time emerges from string theory?
That's really cool.
Sorry. I thought much.
I just want to.
Oh, I'm sorry.
I just want to orient
that's really cool, but I didn't answer to your question.
Well, I just want to orient myself with respect to
you're right.
discourse one hears. Usually, when people talk about combining general relativity with quantum mechanics in any way, they're always expecting, at the Planck scale, stuff like that, for general relativity for the general relativity we're used to, the Einstein equations we're used to break down.
Yes.
Are you saying that's not going to happen?
No, I'm saying that. Yeah, general relativity breaks down at the lower level.
So that there's some regime in which the equations aren't exactly true.
But in fact, when I get to the equation, I'm getting an equation at a large scale.
Good.
Because it's reaching flat.
So it was the word exact confused people in this respect.
Oh.
Okay. Exact seemed to mean independent of scale.
Oh, no, I'm so sorry.
Okay.
No, I'm so sorry. You were right.
Good. Okay.
No. What I meant for exact, it was just because for a while, when I started to go through the mathematical formalism, and they say, well, I have this perturbative regime of a classical action, so my expectation was, well, what I'm going to find is some kind of approximation of the general relativity equation, right? But then I was surprised when I say, wow, but this is really the Ricci flat. So, but that doesn't mean that exact in the sense that you say. It's exact at the large scale. And so we should, and that's the way, I mean, but I want to present this derivation, so I don't know what to do. But I have for let's say 20 minutes more, 15 minutes more.
Yeah.
So this is exactly, I mean, I think there is, I try to formulate this notion of emergence of ordinary spacetime inside this idea of effective, method of effective theories that I suggest you strongly, guys, if you want to really understand. I used a book that I found very, very useful in order to give some kind of, how do you say, substance to my argument. And I want to write down the title here. This is a super cool guy, which is called Gordon Payne, and he wrote a wonderful book on supersymmetry. He doesn't speak about emergence of space-time at all, okay? So this is just my way of reading what he wrote, so probably, maybe he doesn't even agree with the way in which I present his idea. So supersymmetry, something else, I'm sorry, I don't have the book. But Gordon Payne, supersymmetry and revealing the fundamental law and so on, right? So it's you have this effective theory, higher level, and then you have a more fundamental theory, and basically even if that what you get is exact, still it needs input parameters coming out from the lower level. And in this sense, quantum string theory is more fundamental than general relativity or even lower scale theories because it provides those input parameters to the theory, to the higher level theory, which will make the higher level theory able to test its prediction. So I would say that a quantum theory, let's say, is more fundamental than an effective one because it gives the possibility to test the empirical adequacy of the higher level theory. That's my idea of emergence. Very, very weak. And I would say, why just not reduction? Right? It sounds more reduction. Why all these people keep talking about reduction? So please, should I look to the camera? No. Please stop talking about reduction. But emergence. But I think that the notion of reduction brings in some other issue. But no. What should I do? What should I do? Let's go with it. Yeah. Okay. But then let me say something more about reduction. Okay. If it is possible. Two words. I mean. Okay. So for the quantum field theorists in this audience, right? So what do you do with the system of quantum correction? Quantum loop correction is, you can get the equational solution, right? This is standard quantum field theory. So you get equational motion, and you have your classical solution. What is a classical solution in this context? A string sitting there, doing nothing. Right? It's not. But now I want a quantum theory, and I start to perturbate this field, this classical solution of the field. And I will perturbate with, let's call it zeta n, okay? This quantum fluctuation perturbation is a quantum field. It's a quantum field that is interacting. Now it is becoming an interactive quantum field theory, okay? As soon as I start to quantize. Okay, but you see that this kind of perturbation has a reflection on this, because now my dx mu will become what? Let's assume that I choose a system of coordinates, very nice, which is well called the Riemann normal coordinates. I'm not going to tell you what it is, we don't need here. But let's assume that thanks to this, I can expand these two guys in the following way. Which is, what am I doing? Oh, okay. So, d ax mu. Let's just a bit of patience, and then you will see something nice. Just give me the time to write. Okay, this is my crucial guy. Okay, so keep attention to this. Don't forget. Okay, who is this guy? Okay, G mu x. I follow my notes that I wrote down 2 days ago because I don't want to make maybe some stupid mistakes that then make people thinking and we lose the track. Okay, so I just double check. But the last correction was last night. It was 2 o'clock in the morning, so I may have been dreaming also. So there must be some mixed up here. So okay, so here is. Okay, so this guy is an important guy. This is the guy from which we will get the Ricci flux, the Ricci tensor. And this is called, well, it's the curvature of the Riemannian tensor of the metric, so this guy. Okay, so once you replace, because this is how it works, right? Quantize an action. Here, you will get a different action, which I'm not going to write, okay? But you will have something like, okay, I can erase this one. The S, the new S, quantized, S will have the S0, which was the previous part, plus the S quadratic, because there is a quadratic part. What's wrong with this one? This S quadratic, I want to write it down, is like this. Let me, even if you don't get all the formalism, I'm thinking for those philosophers that maybe didn't never study, but I know that a lot of guys you study quantitative theory, right? Also the philosophers of physics. So it's perfect. I mean, okay, so this is my summa. So you see I'm repeating some of the things that are there. Okay, A, B. And here I have the bad guy. Z, B. Let's drop all this index, right? I mean, it's not so important. And then none X, X, A, B. And then, again, U, B, X. Now, the problem here is with the quadratic part is that this part, when I do this one loop correction, I have divergences. Oh, there is a kind of, I would like to talk about avoiding the word propagator. I don't know how many of you knows this word because I want you to stay with me. By the way, so far so good or so and so? Okay. But let's say that this is a bad part of this action because basically the problem is that if you take the what is a propagator after all? It's a probability amplitude, right? So it's the propagator is something like z, let's say sigma, let's call this alpha, z, beta, sigma 1, right? And if sigma goes very, very close to sigma 1, this stuff explodes because okay, let's say in words, okay, so, and this part is responsible of this behavior. What is going on here, when I started to introduce a quadratic quantum modification of the classical action, it is the following. So, sigma and sigma 1 are the position, right, of the fields, or scalar particle, okay, because remember this is a two-dimensional quantum field theory over the worldsheet. So, when there is a divergence, what it is going on is this. Look, here, if we start to talk about interaction at a very, very short distance, everything breaks down because the probability amplitude that tells me how it is possible that a particle stay in sigma ends up later on in sigma 1. If sigma and sigma 1 are really close, we have no information because the probability amplitude goes to infinite. So renormalizing a theory Remember, this was conformal invariant, okay? This was conformal invariant. Renormalizing in theory, which I'm going to do here, is basically, okay, here there is an infinite. Let's get rid of this infinite, introducing a contour term, right? It's one of the ways in which you normalize in quantum theory. There are many, many procedures. They are all equivalent. But the problem is this. When you introduce a contour term and you try to renormalize, it's like if you are introducing a cutoff. So you are saying basically, look, you know what, okay, we have no information on what's going on for very, very tiny distances between sigma and sigma 1, too low, too close. You know what, we establish a threshold, a cutoff, and we just ignore whatever happened, very small cutoff. Whatever happened we just don't care whatever happened below that threshold. And so let's establish this threshold in a way that we can still get some information. Here we cannot because the momentum is too high. It goes to infinity. But can you see the problem about that? I said the theory from which I started was conformal invariant, scale invariant. There is no preferred scale. But if I introduce a cutoff, I'm introducing the dependence of the theory from the scale. And so, yeah, I'm safe. I resolved the problem of divergences, but the quantum theory is not conformal invariant, and we want that theory to be conformal invariant, right? A finite theory cannot have less symmetries than a coarser theory. We want to keep all the good things of what we are modifying. Okay, I don't see any. I'm not receiving many feedback. So is that clear? So far?
We're just not Italian.
I know. So it's 2 hours of nothing for you guys? Oh, so because you're not Italian, you don't understand me?
No, we understand you, we just don't emote as well as you do.
Yeah, you're right. I'm sorry. It's different body language, right? We were talking with David about different body language. Yeah. Okay. So what should I do to kill? Okay, I'll be very, very quick now, okay? So what I want to do, and I prepared last night.
We should finish up within 10 minutes or so.
Really?
People can leave. Yeah.
Okay. Let's do this. We can. Let me just write at this point the magic formula. So, you want to kill the infinite here. So, you renormalize in this way. So you have that your original, let's just focus on the quadratic part, okay? The rest is okay. Sorry. This quadratic will be right. Let's see. An action which is normalized now, in which I got rid of this part. But yeah, it is normalized, but I can have so few information with respect to what I could have had in a full quantum with no divergences. But I want to add a term, which is S infinite. And this S infinite is basically something that I want to show you. Oh no, I need this one. Okay, let me do this in this central part. 10 minutes, right? 10 minutes. Let me write down this S infinite, because from S infinite we can see what I mean. S infinite, I don't want to make mistake, is times of pi. And so you can see it's very similar to part of the integral which was there. A and b, and then you have the x, and then you have this guy, mu half b, and then something that I want, at this point I have 10 minutes, better not to write it, okay? It's the limit of an integral. This limit of an integral basically introduces the cutoff. It's telling me, look, don't worry, you can't go beyond that, so just don't care. Okay, so, and I am in 2 dimensions here, so the idea is, okay, but the problem is that this theory is not conformal invariant, and now I can show that. And is there any option that I can find? Is there something that maybe I can rescue the conformal invariance of this theory, even keeping that as infinite? Okay. I told you that this limit is not computable in an exact form. Now, let's do a little trick to see why it is not conformal invariant and how we could rescue the conformal invariance. Okay? Is that clear? Sounds contradictory? Does it sound contradictory what I'm saying? So I'm saying this is not conformally invariant, how it is, okay? But then we will end up in something that will make us understand that it could be still conformally invariant, so string theories, quantum string theories is a consistent theory if something happens. So let's just modify slightly the dimension of the space. We are in dimension 2. Why am I doing that? Because in order to understand why it is not conformal invariant, I have to understand what this guy is. I don't know. Even if I wrote down what I have here, we would see that we cannot compute that integral. We need to compute that integral. So let's move to this dimension, 2 plus epsilon. And let's rewrite this in dimension 2 plus epsilon. Okay? Something like that. What phi, and then I have b2 plus epsilon sigma, my gamma, gamma b, x, r mu, what it is, mu alpha beta. And now I can compute. It's a kind of dimensional regularization where you cannot compute the limit of an integral in a certain dimension. It is helpful to increase the dimension and then find the solution. But yeah, I can see Chris' face a bit problematic, but I'm going to show you that even if it sounds arbitrary, is that what you're thinking? No? Okay, I'm sorry. I misunderstood. Yeah, I'm sorry. I didn't want to point my finger right at you. You just said you are there, and you always make clever questions, and just, yeah. So. Okay, so now in dimension 2 plus epsilon, this limit can be rewritten in a nice way. Very nice. You will see why. And I mean, this required, how to do it, it required 1 week last winter when I was working on this stuff. But I promise I won't show you how to do from here to here. Okay, now, all right, we have these things. Now we have, let's bring this limit outside. You see the variable of integration here is sigma. I can move this limit as I want. Almost there, okay? Almost there. Now, gamma, x, r. Okay, let's do this. So I have here, look. You see this guy, G alpha beta. I forgot something here. It's mu alpha beta. These two contract, right? So what I can get out of this is my Ricci tensor. Good. And now we have alpha 1 here, alpha 1 somewhere. There it is. Gone. Alpha 1 is gone. All we have is 1 else. Okay, now we are in plus 2, plus epsilon. Let's take the infinitesimal transformation, which I wrote down here, of this guy, of S infinite, infinitesimal conformal transformation. Let's write this one. Gamma, and now I have minus, let's do this, limit epsilon goes to 0, 1.5, and following the rule, right? Our d in our case would be 2 plus epsilon. So I follow the rule, and what I have is an epsilon outside here, and then b 2 plus epsilon sigma, gamma b. You can check if you send this, right? This metric part. you apply this transformation, you will get something that it is non-conformal environment. Okay, where is it? Oh, right, see. And then I have, so, the x, r, mu, 1 over epsilon. So this epsilon here comes out from the infinitesimal conformal transformation that I applied to S infinite in dimension d plus 2. Sorry, 2 plus epsilon. Is that clear? Otherwise, I couldn't have done this, right? Because if d is equal to 2, I have identity. So there is no way. Okay. But now, look here. Well, this is crucial. They cancel each other. So even if it could look that taking the limit epsilon goes to 0, right? I can, this should annihilate this part. Now epsilon dependence is gone. Now let's take the limit. I want to rewrite, okay? Just write down this. So look here, this is fantastic result. I'm taking the limit, epsilon goes to 0, so you have 2. I'm saying, let me write here, if you prefer, I mean, yeah, you can read like this. Okay. What do you notice here? I'm now back to dimension 2, which was the guy I wrote down here. I'm saying that the variation of S infinite of the control term with respect to the infinitesimal conformal transformation is not 0, epsilon is gone, unless magic. Then we get the vacuum solution of Einstein field equation, except in the sense that we now agree. And is this emergence? Well, the quantum stream motion tells to the, I mean, is this emergence? Well, let's see. I said early on, I gave a definition of ontological emergence. We were talking with Chris, and but if I say, okay guys, let's keep talking about reduction and let's just get rid of this stuff of emergence, because it's not emergent, but maybe no. I think we can still talk about emergence in this sense. So the problem I have, okay, maybe it's just my problem, with the notion of reduction is this. When I reduce a theory to, let's say, general relativity reduced to a more fundamental theory, which is string theory, reduction is something that evokes in my mind the following things. So if the properties, physical entities, nomological structure of the reduced theory should be mapped in some sense one-to-one on those structural physical property populating the reducing theory. Reduction is, after all, I mean, it's just talking about bridge, translation from one side to another. And I remember the first 2 weeks we have been talking about cosmological principle, a lot of large-scale property principle, nomological thing, the structure of this. And think to the cosmological principle, right? If I remember well, it was in one of the slides. I think your slide, in which you gave this description that, okay, at a large scale, space appears uniform, and and something else. Now I don't remember the slide, but you gave a description in terms of large scale description. Inside that domain of application, right, of a cosmological theory, those entities, those physical properties have sense, because they are basically they can be formulated only inside a certain length scale, right, or distance scale. So the physical property of a physical system are identified basically, I don't want to use the word nature, by the length scale that the theory introduced. translate the cosmological principle in a length scale like that of string theory. How am I mean, string theory entirely explain, let's say, general relativity. But still there is some room for a notion of novelty, but epistemological novelty. There are entities, nomological structure, principle in the higher level theory, or if you prefer, large distance theory, which cannot be reduced to the lower level entities, not because this is impossible in principle. This is possible in principle. I am a reductionist physicalist in my heart, okay? But it is not possible in practice. It's not computable. And Gordon Kane gives a fantastic, sophisticated description of how the reflective theories relate to each other in this sense. Yeah,
we gotta let people go to lunch.
okay, so I feel like I want to talk about, yes, yeah, categorical respondents.